This code is checking whether the machine learning model treats different work types fairly. It does this by calculating several fairness metrics for four groups: people who never worked, and people in private jobs, and also people who are self-employed, and also the children. The first step, setting up data. The code first sets up the real labels and the model's predicted labels. Then it creates an empty dictionary called fairness matrix to store the results. And for each work type, the code checks if that group exists in the dataset. If it doesn't, it skips to next group. If the group is present, it calculates five key fairness metrics. The first one is demographic parity difference. It measures how differently the model predicts positive outcomes for each group. If this number is high, some groups may be getting more favorable results than others. And the second one is demographic parity ratio. It compares the percentage of positive predictions between groups. If this number is close to 1, the model is treating groups similarly. And the third one is equalized odds difference. It looks at whether the model is making mistakes at different rates for different groups. And the fourth one is equalized odds ratio, similar to the previous one, but as a ratio instead of a difference. Ideally, this should be close to 1 for fairness. And the last one is accuracy. It checks how often the model is right for each group. And all these fairness metrics are saved in the Panda data frame, which is then printed so we can see how fairly the model is performing across different work types. From the fairness metrics output, we can see that the model treats different work type groups very unequally. Here is the key metrics tell us. The demographic parity ratio, work type never worked and work type children have 0 and 0.01, meaning that they are almost never predicted to get positive outcomes. In contrast, work type private has a value of 0.86, which is much closer to fairness. This stress that the model strongly favors people with private jobs while severely disadvantaging those who never worked or are children. And the second one is equalized odds ratio. Work type never worked and work type children have 0, meaning their false positive and false negative rates are highly imbalanced compared to other groups. This indicates the model is making very different types of errors for different groups, which is a major fairness issue. And for the accuracy, all groups have high accuracy, but this doesn't necessarily mean fairness. The work time never worked has 100% accuracy, but that might be because the model never predicts positive outcomes for this group, which is reflected in the DPR and the EOR. Even though the model has high accuracy, it is far from fair. The extreme differences in demographic parity ratio and equalized odds ratio show that there are some groups are almost completely excluded from positive outcomes, which is a major ethical issue. Adjustments need to be made to improve fairness without sacrificing too much accuracy. And this is how we reduce the bias. This code helps make the model fair by ensuring different groups have similar chances of getting positive predictions. It does this using demographic parity, which means the model shouldn't favor one group over another. Firstly, setting up fairness constraints. The code defines demographic parity, meaning different work types should get similar predictions. And the second one is training a fair model. It uses exponential gradient to adjust a random forest model, reducing bias in decision making. And next step is to apply the fairness constraint. The model is trained while checking fairness based on work type private group. And the last step is to make fair predictions. After training, the model make bias adjusted predictions, ensuring work type doesn't unfairly affect results. And for this part, the code use Lime to explain why the model made a specific prediction. We first setting up the explainer and choose a sample to explain, and also generate the explanation. Uh, we also visualized the explanation, use the EXP showing notebook. Uh, this line visualization explains why the model predicted no stroke with 73% confidence and stroke with 27% confidence for this specific case. The key feature spotting no stroke being elderly and very elderly lowers the stroke prediction. A moderate age range also pushed the model towards no stroke. Smoking status and self-employment played a minor role in reducing stroke risk. And the key features supporting stroke is middle-aged status and private work, also overweight BMI, strongly push the model toward predicting stroke. Heart disease and never having worked had no impact. The combined effect of stronger blue features led the model to predict no stroke with high confidence. However, the presence of risk factors like BMI and work type still contributed to a 27 stroke probability. And for the anchor method called explanation, we first set up the explainer and also we choosing a sample to explain. And the last step, we generate the explanation. It prints the anchor role, the key conditions that strongly influence the decision, and also the precision. How often the rule leads to same prediction, and also last one is the coverage. How many similar cases in the dataset follow this rule? And how can we understand the anchor explanation? This output shows the rules the model relies on to make predictions. The anchor rule, the model predicts based on two key conditions. The first one is age, and the another one is not elderly. If these conditions are met, the model almost makes the same prediction, and the precision is 0.97. This means that 97% of the time when these rules apply, the model's prediction stays the same. And the rule applies to 35 of the data, meaning it explains about one-third of the cases. And let's see the permutation importance. This code measures how much each feature impacts model accuracy by randomly shuffling them and checking the drop in performance. The first step is sample data, and second, we calculate permutation importance. And the third one is store and sorting results. And the last one is visualize the importance. This chart shows which features impact the model's accuracy at most. The longer the bar, the more important the feature. The first part is top features. Age and elderly status have the highest impact, meaning the model heavily relies on them for predictions. And BMI, also middle age status and the glucose level are also important, but to a lesser extent. And for the less important features, factors like work type, gender, and hypertension have little influence. Work type, such as never worked and children, has almost zero impact, meaning the model doesn't use them much for decision making.